In section 6.8, we're going to be looking at problems of variation. In the last section, we covered a number of different types of application problems where we ended up with rational equations. We've got another batch of real-world problems, word problems, that we're going to be able to solve now that involve rational equations again. Now, these actually turn out to be quite a bit simpler rational equations than we would have to deal with otherwise, but they are a very useful set of applications. That is, we see these types of variation problems showing up in chemistry, finance, physics, biology, any type of application where you have related quantities working together that both maintain a constant proportion. Those are going to be what we call variation problems. Now we'll look at more detail what I mean by that. So let's take a little closer look at problems of variation. Variation, by definition, is an equation that relates one variable. Let's try that again. Relates one variable to one or more other variables using multiplication or division. Okay, and there's going to be three types. Now, that's not a very clarifying definition, I'll give you that. You'll see a lot better understanding of what these are when we look at the specific types of variation. Namely, when we look in depth at direct variation, we will look at inverse variation, and we're going to look at joint variation. And we'll actually have a combination of these as a possible type of variation as well. So to begin with, when we start looking at direct variation, here's really what we mean. A variable y varies directly with x when the two related variables both increase together or decrease together. Okay, and although I don't say it here, they stay in constant proportion. What that basically means is that, say for example, two quantities we know to be directly related, that is, they vary directly or they're directly proportional to each other. If we have that, then if one doubles, the other one doubles. That is, if it goes up twice as much, the other one's going to double. It's going to go up twice as much. If it gets cut in half, the other one's going to get cut in half. So when they go up together. When one goes down, the other one goes down with it. Now the key words to look for in a word problem that tells you we're going to be looking at direct variation are those two phrases that I just used. One is to say varies directly. That is, something varies directly with something else. Or you might even see it written as this, directly proportional. I've even seen some texts just use the word proportional by itself to describe this. But directly proportional, that's the word we're looking for. You'll see in your homework a number of different examples of direct versus inverse versus joint variation. In this case, I wanted to give you at least one quick example, and maybe you can come up with a couple on your own. In a fixed period of time, that is, if we're talking like over the course of an hour, the distance a car travels varies directly with its speed. Now think about those quantities and confirm to yourself that those are in fact directly proportional, right? If a car travels faster, the distance it's traveling is also going to increase, right? But if you slow down, the distance is going to go down. So they go in the same direction. They move in the same direction together over a fixed period of time. You know, a rather informal example, and probably couldn't quantify it, but I use this example in my classes. Your grades in the course will vary directly with time spent studying. I'm going to leave the other blank empty for you so you can think of some other examples of where two quantities would vary in the same direction. That is, they both increase together or decrease together. Now, more importantly, how are we going to solve different word problems that have these? We need to be able to identify the formula that the variation problem has. For direct variation, the formula always looks like this. It's going to be y is equal to k times x, where k is what's called the constant of proportionality. In general, k is going to be different in each problem. What k basically does is tell you how fast one changes with respect to the other. So, for example, just because I go 2 miles per hour faster doesn't mean I'm going to go 2 miles further. Like if my fixed period of time was 7 hours, increasing my speed by 2 doesn't necessarily increase my distance by a number 2. It may increase it by some factor of 2, some product, multiple of 2. So that's what k tells you, and I'll show you how you actually find the k in these given problems. To solve any variation problem, we start by identifying and labeling the variables. Then we set up or write our variation equation. You saw on the previous page the variation equation for direct variation, and you will see similar formulas for the inverse and the other type, the joint variation. Then you plug in a test case. All of these problems, you'll have one situation where you know both the variables, x and y, and you use that to solve for k. And then what you do after that is rewrite the original equation with the x's and y's back in there, but replace the k. That is, write in the specific value for k, but also leave the variables like the x and the y in the problem. And then you use that equation to answer the question. So here's a quick application of a problem where we have direct proportionality. The amount of drug theophylline given to patients is considered to be directly proportional to the patient's mass. All right, so we've got the amount A, and we've got the patient's mass M. We are given 100 milligrams, that is amount of drug, right? If the boy has a mass of 25 kilograms, that's mass. And then the other question that follows that, or the question that follows that, is how much of the drug should be given to somebody whose mass is 80 kilograms. So first thing we do is we label our variables. Of course, we have A is the amount, M is the mass, and so we know that the amount is directly proportional to the mass. Okay, so whenever y was directly proportional to x, we wrote y is equal to k times x. So if A is directly proportional to m, we're going to write A is equal to k times m. Now let's look at our test case. We are told that for 100 milligrams, that is if A is 100, the mass M is 25. So A equals 100 when M is equal to 25. So plug those in. You'll have 100 is equal to k times 25. So what does k have to be? Just divide both sides by 25, and k is equal to 4. So if you come back up to your variation equation, what that now looks like is A is always 4 times M. Okay, so now we can answer our question. How much the drug should be given to a patient whose mass is 80 kilograms? So we let M equal 80, and A is going to be 4 times 80, or 320, and our units for the amount is milligrams. So that's our dosing. Looking at the second type of variation, we can go ahead and go through the same procedure. Basically, go through the same definitions, keywords to look for, what the formula looks like, and then give us an example. So the second type is inverse variation. When two quantities vary inversely, it means that as one quantity increases, the other decreases. So they go in opposite directions. One value increases, forces the other one to go down. Again, they maintain what we call a constant proportion. The keywords to look for here are varies inversely or inversely proportional. Now here's an example that may not relate to everybody, obviously, because this is an online class, but we've got two cities here that are close by. The main campus of Wayland Baptist University is in Plainview. That's where all the administrative offices for the Wayland system lie, is in Plainview. Our closest kind of big city, if you call 200,000 population big city, is Lubbock, just down the road. It's about 45 miles away. So if I were to say I'm traveling from Lubbock to Plainview, an example of an inverse relationship would be between the time it takes me to get there and my speed. Right? The time it takes me to get from Lubbock to Plainview varies inversely with my speed, because if I increase my speed, the amount of time it takes decreases, and vice versa. If I slow down, if I decrease my speed, the time it takes to get there increases. Okay? So another, like we saw before, informal example might be something like the grade in this class is inversely, I can write inversely proportional to, say, the time spent sleeping through the videos. Surely that's not happening, but you can imagine that if you slept through the videos more often, right, you spent more time sleeping through the videos, your grade is going to go down. If you spend less time sleeping through the lectures, your grade is going to go up. Okay? Now, you could probably think of even better examples, and you will see plenty of examples in the homework that you're doing for this section. Now, a formula for this type of variation is the following. It's y is equal to k divided by x. Whenever y varies inversely with x, it's y is equal to k divided by x. Okay, this is where you go back to the original definition at the very beginning of the chapter, sorry, of the section 6.8, and we defined proportions being those types of equations that involve only multiplication and division, and that's what you see. You see multiplication is direct variation, division is inverse variation. Now the steps are exactly the same as before, right? And I can even scroll up here on my screen and show you the steps we're going to take are the same for all variation problems. That is, we're going to label our variables, write down the variation equation. It's the second step that is different for each problem, because the variation equation will depend on what type of variation we have. But then we plug in the test case, we solve for k. We'll rewrite the equation with the variables and the specific value for k, and then we use the equation to answer the problem. Okay, so let's look at this example right here. We've got that the amount of time it takes a block of ice to melt, right, varies inversely with the water's temperature. Keywords being varies inversely. If the block of ice takes 20 minutes to melt in 60-degree Fahrenheit water, how long will it take to melt in 100-degree Fahrenheit water? So first question you need to answer is, what are my variables? Right, well, the first thing I notice is it's the amount of time it takes the block to melt. So let's let that be time, a lowercase t. Now you could choose anything you want. You could let that be y, you could let that be x, you could let it be any letter that you choose. I'm going to use lowercase t for time, as is a common practice in physics problems like this. And that varies inversely with the water's temperature. Right? So what variable do we want to let that be? It's temperature, it's still t. I'm going to use a capital T. It's easy to tell the difference between a lowercase t and a capital T. So capital T from now on will be temperature in this problem. Okay, so a block of ice takes 20 minutes. Now 20 minutes is time, right? So that is what I have here as my blue. and the time to melt in the temperature of 60-degree water. Okay. Notice how 20 minutes and 60 degrees are together, so they are a test case, and we want to know the answer to whenever it's 100-degree water. Okay, so I've got that the amount of time it takes is inversely proportional. Inversely means divide by that variable. So it's always variable equals k, and then you're going to multiply or divide by something. In this case, we divide because it's inversely. Now our test case. Like I identified here, we know that the time is 20 minutes when the temperature is 60. So 20 is equal to k over 60. Multiply both sides by 60. That gives me 1,200 is equal to k. So that means my now equation looks like this. T is equal to 1,200 divided by whatever my capital T is. And I don't know why I wrote an X here. Of course, I meant that this is capital T. Apologize for that mistake. Make it bold to emphasize that. Now, here's our model equation that we can now use to answer the final question. That is, what's the time it's going to take if the temperature is 100? So let capital T be 100 degrees Fahrenheit. So that means the time is 1,200 divided by 100. Zeros cancel, so I end up with 12 minutes. Joint variation. Let's take a look at that. Now, if one quantity varies directly as the product of two or more other quantities, we call this joint variation. It's very similar to just direct variation, but instead of having one variable directly proportional with another, you have one variable that's directly proportional with the product of two or more. So you now have three or more variables in the problem. And of course the keywords to look for in this would be joint variation. It's just, that's the way it's going to be stated. So, or jointly varies. Which is what I probably have said. Jointly varies. Okay, now if a variable y varies jointly with x and z, then here's how we write the formula. It's y equals k. You always start with y equals k, or with one variable equals k. And because it's joint, it's the same as direct, it's multiply, but you just keep multiplying. There's always going to be just one k. Now here's an example of where you might see joint variation showing up. We have that the area of a triangle varies jointly with its base and height. If the area of a triangle is 48 square inches, when its base is 12 and its height is 8, find the area of the triangles whose height is 20 and whose base is 15. So we notice right away these keywords, varies jointly, and we got to label our variables. So let's highlight what variables we have. We have area, varies jointly with the base, and the height. So we have three variables. Let's label them as A for area, B for base, and H for height. Now we're given a test case. Now which values do we know? What's the area that we know? Well, we know that the area is 48 inches square, or square inches. We know that the base is 12 inches, and we know that the height is 8 inches. Okay? And then we're asked to find the area if we know that the base is 15 and the height is 20. So we've identified our variables. Let's write down our variation equation. A varies jointly, so always A equals K. And since it varies jointly, it's just going to be multiplied, base times height. Our test case reveals that A is 48 when B is 12 and H is 8. So plug all those in to your variation equation. 48 equals K times 12 times 8. So 48 equals 96 times K. Dividing both sides by 96 and simplifying means that K is 1/2, right? Just take 40 out of both the top and bottom. That's what you end up with. 1/2. So the area of a triangle is equal to 1/2 base times height. Okay? Alright, then let's answer the question. We're going to let B be 15 and H be 20. So A is 1/2 times 15 times 20. 1/2 of 20 is 10, so 10 times 15 is 150. So 150. The area units in this case are in square inches, so inches squared. That's my area. All done by looking at just the variation between the variables in this problem. In summary, our formulas look like this. Direct variation is y is equal to k times x. Inverse variation is y is equal to k over x. And joint variation is y is equal to k times x times z. Now, there's no reason why we can't have more than one of these types of variations occurring in the same problem. All you've got to remember is direct or joint are multiplication problems, and the inverse is division problem. So let's look at this example right here. We have the statement that A varies directly with B and inversely with C. Okay? There's always just one K, so I always start this the same way. A equals K. And if it's directly with B, then directly means multiply. So K times B. But inversely means C. So that's division. So I'll divide this all by C. There is your variation equation when that is your statement of variation. Now what if I said A varies jointly with R1, R2, and inversely is the square of L? Now, varies jointly, there's a key phrase, and inversely is another key phrase, but don't forget about what this here would mean. So A varies, so A equals K. If it's jointly, again, it's multiply. So we're going to have R1. Now, don't let this subscript confuse you. We haven't used this kind of notation much in this class. All the R1 means, it doesn't mean raised to a power or anything. It just means that's the name of the variable. Okay, it's just like if I had used X and Y, I'm using R1 as a variable, R2 as a variable. So subscript's just part of the name. It doesn't mean do anything to the R. So I'm just going to write R1, R2, divided by, because it's inversely, and the square of L. How do you write the square of L? Well, it's L squared. That is how we would translate this statement into its variation equation. So let's look at a word problem that might have multiple variations in the same problem. The owners of the Freeport pretzel shop find that their weekly sales of pretzels vary directly with their advertising budget and inversely with their pretzel price. When their advertising budget is $500, their price is $2, then they sell 4,800 pretzels. We want to find their expected sales if they bump their advertising budget up to $600 but drop their price to $1.20. Right? Begin by identifying, first of all, that it's a variation problem. You see varies directly. There's the key words. You also see inversely. Now, what quantities are involved? Well, we have the weekly sales, right? We have their advertising budget, and we have their pretzel price. So let's label those with some variables. Weekly sales, let's call it S. That's how many pretzels they sell. Let's call their advertising budget A, and let's call their pretzel price P. Now write down the variation equation. Weekly sales vary, so S equals K, directly with their advertising budget, so times A, and inversely with their price. Now what test case do we have? We have that their advertising budget of $500 and their price of $2 gives me 4,800 pretzels. So advertising budget's $500, their price is $2. Okay, so test case, we have S is 4,800, advertising budget's 500, price is 2. So that means 4,800 is equal to unknown K times 500 divided by 2. So 2 goes into 500 250 times. So that's 4,800 equals 250K. Divide both sides by 250. And I'm going to go to my calculator now and I'll divide that out. I get 19.2. So now rewrite your variation equation. You have S is 19.2 times the advertising budget divided by the pretzel price. Now let's answer the question. The question says, let the advertising budget, which is A, my highlight up here is green, be 600, and then let my pretzel price P be 1.2 or $1.20. So A is going to be 600, P is going to be 1.2, so the number cells is going to be 19.2 times 600 divided by 1.2. And I'm going to go to my calculator and plug all that in. 9.2 times 600, all divided by 1.2. I get 9,600 pretzels. Okay, by spending an extra $100 and lowering our price by 80 cents, we have doubled the number of pretzels that we are able to sell. Okay? All right, those are variation problems, and that ends Chapter 6, covering rational expressions. By the way, the reason 6.8, I didn't ever really talk about this, but 6.8 is part of Chapter 6 is that the inverse variation problems involve fractions. So that's really the only place that that kind of problem shows up, that is that this is a fraction problem. We don't have to use any of our LCD techniques to really solve these. This is just a little extra application to kind of throw in here at the end that gives you a lot of applications, a lot of types of scenarios that we can handle with this model, but we don't actually even have to use some of the techniques that we covered earlier in Chapter 6. All right? Okay, that's the end of Chapter 6.